This presentation is on the measurement of substation load current using an Android phone with collaborators from Loughborough University and Western Power Distribution. So why do we want to measure the load current using an Android phone? Well, to enable the smart grid and all its associated functionality, it's necessary to have widespread rollout of monitoring across low voltage distribution networks. However, this can be expensive, and the estimate is about £1,200 per substation. This is because most traditional monitoring devices use Rogowski coils, which can only measure the current in a single phase cable. And therefore, to monitor what's happening on the LV distribution network, you need a Rogowski coil for each feeder output and for each phase of the current. This project and the paper was about whether it was possible to use low-cost consumer products, somewhere at less than £150 per device, to monitor the substation load. And to this end, this paper looks at whether it's possible to use an Android phone for such functionality. So there are lots of different methods of load estimation. The most common and commercial is the Rogowski coils. Then there are other low-cost variants of different types of coils, optical methods, thermal analysis, more recently arrays of Hall effect sensors, and MEMS, so microelectronic mechanical sensors in phones. And in this case, we're going to specifically look at the use of a magnetometer. So magnetometers are designed to measure the Earth's magnetic field. Now, in phones with Android version 6 and upwards, there's a flag that indicates whether the phone has a high fidelity sensor. And if it does, it means that the sensor has a minimum range of plus or minus 900 microtesla with an accuracy of 0.6 microtesla. Smartphones that have magnetometers are also useful as data loggers, and they have communication capability. So if we have the current in a cable, we can estimate what the field is from B is mu I over 2 pi r. And if we have a phone within that field, we can register it on a couple of the axes of the phone. So there are 3 axes on the phone, x-axis, y-axis, and z-axis. And if we put the phone parallel to the cable, then we only need to worry about the x and z components. What we also need to be careful about is the internal calibration setting, which can be deactivated. So if you look at the magnetic field, the raw data that comes in from a phone, and this is from a phone that was on our test rig, you can see that as we increase the current, the readings sort of jumped about all over the place. So, and as we turned the readings off, and although they seem to bounce all over the place, if you actually plot the X and Z components, you can see that these are not changing with respect to each other unless you're changing the set point. So what you can see is a set of ellipses with the same dimensions for 20 amps, 40 amp, 60 amp, 80 amp, but actually what's happening is that the DC component, or there's an offset of that ellipse is happening. So if we can remove that DC component and analyze that ellipse, and it'll tell us what the magnetic field is. And so we use principal component analysis to enable us to do that. It's not only possible to use a phone to look at a single core cable, we can also look at 3 core cables. So for example, here we have a 3 core sectored cable with 3 phases, red, yellow and blue. And if we align the phone with the red phase, then we can work out the relationship between the current and the field in the X and the Z directions. We have to assume a balanced system. So for example, if we look at the field at the phone sensor due to a current in the yellow phase, the X component is mu naught I sine omega t minus 2 pi upon 3, so the phase shift in the current, over 2 pi R4, so the distance between the yellow core and the sensor, times cos phi for the X component and sine phi for the Z component. If you take into account the current also from the blue phase and the red phase, which will be in the X direction only, then you can simplify the expression to give you an expression very similar to a single core cable, where I is equal to 2 pi times the flux density over a geometric factor times mu naught. And the geometric factor is dependent on the distance to the red phase and the distance to the yellow-blue phase. So how does the process work? Well, We use the phone to get the current phone readings of BX and BZ, and we also need this in conjunction with the values from the last reading. Then we calculate the change in time since the last reading. This is because the phone records data asynchronously, so it's not a set time period between the readings. Then we calculate where the center is from the last readings, and this represents the center of the ellipse. So we can then work out from that what the current BX and BZ values are by subtracting this offset value. And we use an exponential moving average to enable us to get a good average value of the current B. And from B, we can calculate I. We can also calculate all of the ellipse dimensions, and we can use these to error check the results that we've got. And then we can update the values. So our current reading becomes our last reading in the next iteration, and upload the values to a server. In terms of hardware, the costs are very low. So we were using a Sony Xperia M4 phone, which you can buy on eBay for about £50 when we wrote the paper, but now it's about £40. We had a 3D printed clamp part, so that's this little clear device here that screws into a commercial phone holder. So this is the off-the-shelf phone holder, and it has cable ties through it, and you can just cable tie the phone holder to the cable. And then the other thing we need is a power supply for the phone to stop it running out of charge. And when you add all those up together, then obviously you get a cost that's much less than £150. We've tested the phone at two different places. So first of all, we tested it on a rig that we had in the lab. So in the rig, we have a three-phase 400-volt supply that feeds a variac that's 5 to 400 volts. So we can get a range of voltages that's manually. And then that goes through a step-down transformer to give us a high current. So we can generate currents of balance currents of 0 to 120 amps into a 3-core cable, which we then short circuit at the end, and that's at low voltage. We used the rig to calibrate the sensors because the location of the sensor itself isn't known. And then we moved the setup to a substation on the Loughborough campus. And we put the phone in two locations at two different times on the 11 kV cable going into the transformer. So there's a 11 kV cable, and also on a single core cable that's coming out of the transformer feeder. This is the results for the single phase cable. So we have a Fluke power quality meter with a Rogowski coil on the blue phase, and this is shown in blue. And then we have our measured field using the Sony in microteslas with a scale on the right hand side, and the calculated current from B equals mu I over 2 pi r. And that you can see that gives us fairly close results. And in particular, we have a compressor load, and we can easily detect when the compressor load is turning on and off. For the 11 kV cable, it's slightly harder because we only have the Rogowski coils to compare against. So we had Rogowski coils on all the low voltage blue phase feeders coming out of the transformer, and we summed these together. And then we have the measured field on the HV side, and we have the calculated current that's then referred to the LV side of the transformer. So this is the current on the LV side of the transformer, and it's the total current that's leaving the board. This is, again, it's fairly accurate at the peak. It's not so accurate down at low currents, and this is because 25 amps of current is equal to about 3 amps of current on the HV side. So we're at very low levels of current, and it means that the field measurement is not as accurate as we'd like. So if we were to conclude, we've used a mobile phone to measure the load current. The load current was very peaky, which was a compressor turning on and off, and the loading at the substation was on the low side. It would have been better for us if we'd had a higher current. Logging values and timestamping data were available. It needs to be aware that data isn't logged synchronously, and there's around a 2-second delay from real time. So that's for the sensor, the calculations, uploading the data to the server, and then getting the data from the server. And we used this in conjunction with Earth's steel wired armored cable. So all in all, it's a promising technique, but we needed to pre-calibrate the phone in the rig because it wasn't clear where the sensor was, and more work is needed on accuracy, the effective armor, and different cable types. What I would say is that the code for the phone is available on GitHub for free if you would like to download it onto your Android phones. And it's also in the final closeout report for Project Deduce in just in text format that can be copied and pasted. So if you would like to use this, then please, go ahead and pick it up. Thank you very much.